Okay, so we'll call the meeting to order, the April monthly meeting, and we usually start off with the March 2026 meeting minutes. They were posted on our website in the members area. If anybody has actually read them or not, they want to make any changes or errors or omissions, speak up now. Nope. Okay. Can I get a motion to have those minutes read into the record? Okay, now I can't see anybody. Oh, Murray Paulson made the motion. Do we have a seconder? Okay, thank you. All in favor? Aye. Good. All opposed? None. Okay, motion carried. Okay, next on our list is Jeff Whiten and the treasurer's report. So Jeff will be here momentarily.
Good evening, everyone. So it was a slow month, a really slow month, as is typically the case in the spring at the center. But just a quick update. So in the general account, we saw one major transaction go through, and that was the pre-booking for the start party. So every year, I think right on the crack of midnight, Rick Brom goes in there and he books everything in the northern side of the campground. So he got that booked for us. So we, as a center, we pay for that in advance, and then that's reimbursed back to us as they go on sale for the start party. But we started the month with a balance of about $84,000. We ended the month with a balance of $80,714 in the general fund. We had about $500 flow into that account from membership dues, and we had another roughly $300 from a small equipment sale through the month that went through. We also had some minor expenses for meeting refreshments and library expenses. A casino account, once again, very slow. As you can see, our casino account balance continues to dip down. We're now in the $50,000 range. I expect that will bottom out low 40,000s before our casino in June, and then of course we'll replenish that bank account, that account that we use for a lot of our investments and program expenses out of that casino account. So we started the month at 54,585, ended the month at 54,210. We had some, minor B&LO operations expenses, and we had our annual science fair prize that cleared that account last month for $300. The Bob Drew Fund was unchanged, so there was nothing that was put against the Bob Drew Fund, and there still is a little bit amount of money left in that account, about $1,200, that is sitting there for use on the UDT, and I think the BAMT is the other thing that those funds have been dedicated to. Questions? There's one other thing you told. Oh yeah. So some of you may have been here, I'm not sure, but we modified our, what do we call it, expenditure proposal system a couple of months ago, when council adopted a new policy on how we, as a center, as members of this center, put forward ideas for capital expenditures throughout the course of the year. And one of the major changes to the system is that we have an intake process now twice per year. So we have an intake in the spring, and then we have an intake around the budget period in the fall. So that spring intake is April. So council will meet at April. What 27th? April 27th, and I think we have 2 expenditure proposals that are already in-house. If you do have ideas and you're interested in having the center consider one of those ideas for implementation, we've posted the policy and the necessary form that you need on the website. You just go in, it's fairly self-explanatory. go through that proposal, and we've got a little committee that will then help you get that proposal ready to deliver to council, and then it'll be considered in April. If that's too quick for you, well, we're going to do it again in the fall. So we'll also have an opportunity. And this is just a way that all of us then can participate in, advancing cool ideas for the center. And if, as a matter of fact, the plane wave came out of this very same proposal, that idea to establish the new imaging project out at BNLO came out of a very similar process. It's just a member like you that had an idea, gathered some people together, got it approved by council, brought it to membership, got it approved by the membership, and now they've put together a committee to advance that project. Okay, questions? Alrighty.
Thanks, Jeff. Okay. So moving on to our guest speaker for this evening, we have Sharon Morthink will be coming up to introduce Dr. Pamela Freeman.
Thank you very much. It's really wonderful to be able to introduce Pamela to you today. She's originally from Edmonton, and she did her honors astrophysics degree at the University of Alberta. After graduating, she moved to Calgary and did an MSc and PhD in astrophysics there at University of Calgary. And her PhD thesis is on star formation, which involves a lot of the chemistry of the interstellar medium. And she's now considered to be an expert in astrochemistry, and she has a research position in Mexico. So unfortunately, she was not able to actually join us here in Edmonton for this meeting. So she's in Mexico somewhere and enjoying the much better weather, I'm sure. And she's going to be giving her talk by Zoom. I'm hoping that at some point she will be able to come back to Edmonton, and maybe we'll get her to talk in person at some point. So please join me in welcoming Pamela.
Everyone, can you hear me?
Yes, we can.
Amazing. Thank you so much for the kind introduction, Sharon. I'm going to share my screen now. Again, thank you so much for the opportunity to share a little bit about my research in astrochemistry. Again, that was a very kind introduction, Sharon. It's my pleasure to be here. I do wish I could be there in person, and hopefully one day I'll have the chance to. Edmonton always does draw me back, so I'm sure it's just a matter of time. So just to flesh out my research journey a little bit more, I did get my start at the University of Alberta. Sharon was actually my first professor in astrophysics at the U of A. And then it was Eric Kozlowski and Greg Sivakov who introduced me to radio astronomy and astrophysics research. And so it's really them that I have to thank for getting me started on this path. Then the observatory that I got the amazing opportunity to work at during my master's was the Dominion Radio Astrophysical Observatory out in Penticton, just imaged here. Highly recommend if you're ever in the area to go and see if you can get a tour out there. But then I really got started in astrochemistry during my PhD with my supervisor, Renee Plume, pictured just in the green shirt here. And so that's really what I'm going to be talking about today, astrochemistry, the study of molecules in space, and how that really plays into our understanding of star formation and our own cosmic origins. But during my time in research, I did have two little short stints in science outreach. The first was a science communication internship at the European Southern Observatory, and then a little short stint at TUSI. So I can just imagine you all sitting there in the planetarium. Hi, Frank, and hi, Jewel, if you're there. I really wish I could be there. But again, happy to be having the chance to talk here. So I was wondering where to start this presentation, and why not start it all the way back at the Big Bang or near the Big Bang. Soon after the Big Bang, almost the very beginning, the universe was just a soup of hydrogen and helium nuclei. This was the at the beginning, the only ordinary matter that we knew in the universe was hydrogen and helium. Mostly hydrogen, a little bit of helium, and a tiny, tiny little bit of lithium. But the universe that we see today is very different from that, even in the elemental composition, in the atomic composition. And this is partly due to stars. So stars change this atomic makeup through both their lives and their deaths. So we have two different types of stars that we like to classify: the sun-like stars, stars with masses about the same size as our own sun, and then massive stars, stars that are more than about 8 to 10 times the mass of our sun. These stars, during what we call the main sequence of their life, the main part of their life, will fuse hydrogen into helium. And those elements can also fuse to form heavier and heavier elements. Massive stars will be able to fuse elements a little bit more massive because of their size, their temperature, their very energetic life. But also, we have these processes during their stellar death where we get even more energetic events that can create even heavier elements, and that's in our supernova. So these processes are very important to understanding the elements that we see in our universe today. And I just want to take a little side note that 100 years ago, in 1925, it was Cecilia Payne-Gaspochin's doctoral thesis that outlined that stars are made of primarily hydrogen and helium. This is unlike Earth. So at the time, people thought that stars were made up of the same thing that Earth was. Earth has a lot of iron, silicon, oxygen, but stars being made mostly of hydrogen and helium was a game changer. So this really started off our understanding of kind of elements in the universe and how stars really play an important process into what we see today. And so what we know now is we have created our own version of the periodic table in astronomy to understand where these elements come from. So as mentioned before, the two at the top here, hydrogen and helium, those we see in our universe from the Big Bang. That is really from the very beginning of the universe, or near the very beginning of the universe. But for elements like lithium, carbon, nitrogen, why we see those in our universe is because they were expelled back into galaxies from dying low mass stars. Elements like oxygen, fluorine, silicon, phosphorus, those elements are expelled back into galaxies from dying high mass stars. Elements like sulfur, calcium, those are from high mass stars, but also from the supernovae during stellar death. And so we can look at all of these elements and start to pick apart where they come from, why they exist in the abundances that we see them in today. And so we have this understanding of kind of the building blocks of molecules and of life. But again, 100 years, one more part before I get back to history. If you change the periodic table a little bit to actually look at how abundant these elements are by number fraction, so by the number of atoms that exist in the universe, hydrogen by far is the most abundant. Helium is about a factor of 10 lower. Carbon, nitrogen, oxygen, probably about 10,000 times lower than what we would see in hydrogen, and the rest of the elements even smaller than that. So in astronomy, we call anything that is not hydrogen and helium a metal, because really their presence in our universe is much, much smaller than what we would see of hydrogen and helium. So we tend to lump them all together. Don't tell the chemists. Back to history, again, about 100 years ago in 1926, Sir Arthur Eddington noted, "It is difficult to admit the existence of molecules in interstellar space, because when once a molecule becomes dissociated, there seems no chance of the atoms joining up again." So what he is saying here is just interstellar space is so diffuse, it's it has such a low density that the chance of atoms coming together and forming molecules is really, really low, almost non-existent. So in this time that we were starting to understand what stars were made of, what the universe is made of, molecules were not a part of the picture. It didn't take long, though, before the first molecules in interstellar space were discovered. This was about a decade later. The first molecules that were detected in the interstellar medium, so in the space between the stars, were CH, CN, the ion CH+, and these were all observed by optical instruments within the Mount Wilson Observatory, pictured here in California. So a couple of papers from 1937 and 1940 were really important in identifying these molecules in the data from Mount Wilson Observatory. So I want to take a little journey into how we actually observe these molecules. We know they're there. How are we going to observe them? Here is a look at the electromagnetic spectrum. So the light that we can both see with our eyes and light that we can't see with our eyes. We have visible light here. We have ultraviolet, X-rays, and gamma rays that are more energetic past the blue part of the visible light spectrum. Then we have infrared light and radio light past the red side of the optical spectrum at longer wavelengths and lower frequencies. Just to note, microwaves sometimes and sometimes do not get lumped into radio waves. But here, the difference, we're just doing infrared and radio on the red side of the visible spectrum. And depending on what kind of light we're looking at, our telescopes will be built differently. For visible light and for radio light, we can see this light coming from the universe from the ground. So this light can pass through the atmosphere with a little bit of distortion, but for the most part, it gets through, being able to be picked up by our instruments. If you're looking at infrared, ultraviolet, X-rays, or gamma rays, you want your instruments to be above the atmosphere because for that, it will be absorbed or blocked by the atmosphere. But for observing molecules, there are three important places that we would want to look. One is in visible light. So you might remember, this is probably harkening back to high school chemistry and physics, where you can see electronic transitions. So we have these different energy states in atoms or in molecules, depending on the electron configuration. If those electrons change their state, they can either absorb or emit light. And this light corresponds to that specific level of energy that is changed in that transition. So if you're looking at optical spectra, if you're kind of looking at elements across a continuous rainbow, it might look something like this. So calcium, sodium, and iron each have their own unique fingerprint based on their transitions. So if I were to look at a spectrum to disentangle light into its colors and look at its spectrum, what it's made up of, and I saw this unique fingerprint, I would know that calcium's there. Same thing for sodium. If I saw this pattern, I would know sodium's there. Same thing for iron. And just to give you an idea of the idea of spectra. The second important part where we would want to look in light is infrared light. This is where what we call vibrational transitions are. So this is just another change in energy in the molecule due to either stretching or bending. This happens with lower energy than the electronic transitions, so we would see them in infrared light. And the last one we want to look at is called rotational transitions, molecules rotating around their axes. And again, this is just a change in the energy state of that molecule. This is even lower energy than those transitions in infrared, so we see them in radio waves. So radio waves and infrared waves are very, very useful in order to study molecules in space. So moving into radio astronomy, radio really became huge for astrochemistry pretty early on. In 1944, it was first predicted by Henrik van der Hulst that hydrogen emitted radio waves with a 21 centimeter wavelength. So that's at 1.4 gigahertz. That is right in the radio range that we can see here on Earth. But it took until 1951 for it to actually be detected by two different teams, Harold Owen and Edward Purcell, and then Jan Hendrik Oort and Alex Mueller. And so this really started our understanding of galactic structure, of what the universe is made of, because hydrogen, again, is that most abundant atom. But again, I want to talk about molecules in this. You're probably wondering why I'm spending so much time on atoms, but since they are the makeup of molecules, this history, I think, is really important to understand how it developed. And so we have here 1951, atomic hydrogen being detected in the interstellar medium. Just over a decade later, we have OH, our first molecule to be detected in radio astronomy. And then by the end of that decade, by coming up to 1970, many molecules were starting to be detected. So we had things like, more familiar to us, ammonia, water, formaldehyde, methanol, carbon monoxide. And that really was the start of exponential growth in detecting molecules in interstellar space. In 2026, we have over 300 molecules detected, and a lot that are very familiar to us. So Brett McGuire in our field has been doing some amazing work cataloging these molecules and giving a census of them. So the last one published in 2021, this is the suite of all of the molecules we knew of in interstellar space. And this is just a large list, probably very small on your screen, but what I want to point out is this chunk here. This is all of the molecules that have 6 or more atoms in them. All of these molecules with 6 or more atoms in them has carbon, meaning all of these molecules are organic. And so this is really interesting. We're seeing a lot of similar molecules to what we would see here on Earth. Carbon is a huge basis for life here on Earth, and carbon is a huge basis for interstellar chemistry as well. And so we can use these molecules in order to learn a lot about the physical environments that we're seeing in our galaxy in the interstellar medium, and also have a look at the evolution of why these molecules that we see have been formed. And so we can't necessarily look at one molecule and be like, I see this in this cloud and it's for this specific reason. We have to take it in context of the environment, to take what we know about the molecule and what we know of the physical environment to start to piece together an idea of how it got there. There are some caveats to that. There are some molecules that are very useful for certain things. For example, N2H plus in this third column here is one of those molecules that we can see in cold and dark clouds. So you can see N2H plus is quite bright. And if we were to see that same source in visible light, it would be quite dark. So it's a good tracer of cold and dark clouds. With HCN, it's also a good indicator of star form regions. So again, dense clouds that could be collapsing to form stars. We also have in this fifth column here, we start to have these large organic molecules, and those tend to be seen a lot in the hot regions around newly forming stars. And so some of these molecules do give us a little bit of an idea of the environment they come from, just because they're there, but we do have to do a little bit of work to tease out why they're there. So this is just a first overview of some of the regions that you could look at in, say, visible light from their visible light or from their dust. And the bottom would be what we would see in that same source in a specific molecule. So really there is a whole lot of information that we can gather from interstellar molecules. So some of these categories, it's kind of useful to start categorizing these molecules because their formation routes could be similar, or the way that they give us information could be similar. And so I just want to point out two of the common groups that we talk about. The first I've already mentioned. I have on my left here complex organic molecules. So these are molecules that have more than 6 atoms, or 6 or more atoms in them. They have carbon in them, and typically they're formed from regions that are rich in carbon monoxide. And so examples of those are methanol or ethanol, things that we would see here on Earth. And the other category is carbon chain molecules. So these can be complex or not complex. They can be smaller or larger, but typically they have just links of carbon within them. And these carbons would have potentially double or triple bonds between them in order to create that chain. Some of the examples I have here is of propane. So these are really interesting molecules because they are familiar here to us on Earth, and they could be potentially prebiotic molecules. More on that soon. And so to give you another idea of how we look at this data, I showed you a visual of the optical spectra before, what you might have seen before in terms of identifying elements, say, in the sun. If I were to look at radio data that I collected, it might look something like this. All of these little squiggles, if they're above what we call the noise floor, above our noise, if they're a real signal, we can start to do the same process of looking at these molecules, looking at their spectral fingerprint, their unique barcode that we use to identify them, and start matching these spikes to different molecules. So across this whole spectrum, we have lots of complex organics, also some unidentified lines. That's a huge part in radio astronomy now, is we're seeing some things and we have no idea of what to assign them. But again, there will be a wealth of information pulling out these spectra and using these molecules, the information that we get from the spectra, to go back and figure out what physical environment they came from, what their transition tells us about the energy of that region or the density of that region. Lots of information in here. I want to look at another part of the spectra in terms of how we observe them. Because again, if you look at a continuous rainbow, say after a rainstorm, you would see the suite of visible light, all the colors from red down to blue. That is what we see when you have a hot source and you split up that light, that white light, into all of its constituent colors. If I have that same hot source and it passes through a colder object, like a cold gas cloud, the atoms and molecules in that cloud can absorb some of that light, leaving their unique spectral fingerprint on the rainbow of light that we would see with our telescopes, with our instruments. And we call that an absorption spectrum. So in this, I don't just have a clean rainbow, I have these lines that indicate what molecules or atoms are in that cloud. Similarly, if the atoms and the molecules in a cloud gave off that same energy, gave off that light, we would see it in emission. If we had no background source that was giving us that complete rainbow spectrum, we would just see a kind of a blank background, and then we would have our spectral fingerprints coming through in very certain kinds of light. And we would do our detective work in order to figure out what kinds of atoms or molecules are there. So this is how we do the observational side of astrochemistry. Astrochemistry, though, is a combination of lab work, computer modeling, and these observations. So we need the lab work in order to figure out what frequencies or what energies we would expect these molecules to be at. We wouldn't just know based off of guessing, say what frequencies methanol would emit at. There is very important lab work that is done in order to figure out where we would expect to see certain molecules because each molecule has its own unique spectral fingerprint. We can also use lab work to figure out how molecules react with each other in space. So we can try to recreate the conditions in interstellar space, the same temperatures and densities, to the best of our ability, and figure out how these molecules could potentially react to form what we see. This is also done in computer modeling. So if we know the reaction rates or we know what conditions we might need in order to have those reactions, we can put them into a computer model and have it spit out what it would expect to see. And we can compare that to our observations, see if what we understand theoretically about molecules and about chemistry, chemical reactions, see if it actually corresponds to what we're seeing in space. But for this talk, I will be talking mostly, as I have been, about observations, since that is my area of work. But just note, this is a very interdisciplinary field, and we wouldn't be where we are today without the work that's being done in the labs and by theoreticians. So what do these molecules tell us about space? And how do we actually get these molecules? So in between the stars in our galaxy, that interstellar space is not empty. It is filled with clouds of gas and dust. And these clouds can collapse to form new stars. So we have these molecular clouds, again, filled with gas and dust. And by dust, I mean very small grains that are typically carbonaceous or silicate based. So you can kind of think of them as like a graphite or like sand, just very, very, very small, floating around in space. So these clouds can collapse upon themselves, and if gravity overcomes all of the balancing forces in these clouds, they start to form what we call protostars, so hot and dense objects that are going to become stars but are not there yet. Around these protostars, within that cloud, the material falling upon them, or the material collecting onto them, form accretion disks. That is how matter starts to collect around this compact, dense object that will become a star. And eventually, those disks will form planets, and we will end up with our star and planetary system, similar to what we see in our solar system today. Along this entire process, the kind of dynamic evolution of it creates an evolving catalog of molecules. So we can look at all of these different stages, try to figure out what molecules we're seeing and why they're there. I'm going to step through a couple of these stages. So first, we have these dark and cold pre-stellar clouds. So the clouds that are going to be forming stars, but have not yet. They're going to be collapsing under the force of gravity, but they haven't really formed that hot and dense compact object that I would call a protostar, or we would call a protostar. But in these clouds, you can still have a lot going on, even though they're so cold. And by cold, I mean about 10 Kelvin, very, very cold. So here you have some gas molecules that will turn from the gas phase into the solid phase. They will freeze out onto our grains, our dust grains. We will also have, surprisingly to a lot of astronomers who found this at the beginning, we will also have some cold gas phase reactions. We will have molecules that are forming in the gas phase, but typically reactions that don't need a lot of energy because there isn't a lot of energy in these cold clouds to give to these molecular reactions. And so just note these gas phase molecules are observed with radio telescopes. So they'll be rotating in space, giving off light, absorbing light. And so we see them with radio dishes, like the Green Bank telescope in West Virginia, pictured here. Solid phase molecules, on the other hand, the molecules that we are seeing on grain surfaces, we need to observe those with infrared telescopes like the JWST. So molecules will be vibrating on the grain surfaces, giving off energy, and we can see that with our infrared telescopes. JWST has been a huge player in this field already, even though it's only been around for a few years, and the results coming from it are very exciting to see. And so this pre-stellar stage is very important because we do have those molecules freezing out onto grain surfaces. And to kind of throw back to Sir Arthur Eddington, who was wondering how atoms in space could actually meet each other to form molecules, grain surfaces act as that meeting spot. We have atoms and small molecules that are able to connect on grain surfaces and start to build larger and larger molecules. So this is a really important process because this could be the starting point for the molecules that we see later on in the star formation process. So moving on to the next stage where we start to have the protostellar object, this compact, hot object that starts to heat the region around it. So this is an artist's impression of a protostellar system. We have a hot and compact object at the center. It's still surrounded by a cloud of, by some gas and dust. It's got an accretion disk here. And we also have these very energetic outflows. And so there's a lot going on in the system that we could start to see some more dynamics, more complex chemistry potentially happening. Here, there's a little bit more energy in the gas phase due to the protostar heating up the region for more gas phase reactions to happen. So there's a lot happening in that hot gas. And I should clarify, by warm and by hot, I mean tens of kelvins or hundreds of kelvins. So again, not necessarily warm or hot as we would define it here on Earth. So we can start to see some more reactions being possible in the gas phase due to the input of energy. But we also have a potential evaporation of the molecules on the grain surfaces back into the gas phase. So those reactions that we could have seen in the pre-stellar phase happening on those grain surfaces are now released back into the gas. Maybe because it's gotten hot enough that they have energy to be released off from their bind to the grain surface. Maybe they've been sputtered by the outflow, just kind of knocking the grain apart in order to get those molecules off of the grain surface. We start to see a lot happening here. Lots of complex organics seen in these hot sources. One very interesting molecule that was found, I think a couple of decades ago now, is glycolaldehyde. The reason why I bring this one up, aside from the other molecules I mentioned, like methanol, ethanol, things that we would know here, is glycolaldehyde is a sugar-related molecule. So it has been in the headlines quite a bit because it's familiar now to the processes that we know here on Earth that could start building what we understand life needs or what life has. Skip like this. And so after that protostellar stage, when the protostar has started to dissipate its parent cloud, and we start to see more of the disk clearly, and the disk having a little more structure in terms of forming rings or forming planetesimals, we have, again, a lot going on in this stage. And one really big question about this stage is if molecules are inherited from those previous stages, or if the chemical library that we see in this source is reset. If they've started from, if these sources have kind of started from scratch and have started to form a new library of molecules. So if you look at the disk, there are lots of layers to it. So sometimes these disks can be very hard to study. So we have this central object, the newly to be star, accreting material from around it, but also when it's giving off radiation, it can affect the outer layers of these disks. So they're what they're called like light dominated or photon dominated. That can really determine what molecules we would see there. But once you get to the more protected layer in the middle here in yellow, there's a very rich molecular chemistry that we're seeing there. And this is because it's shielded from the radiation that we're getting from that protostar, but it still has some heat in order to have those molecular reactions or to have them be inherited from the previous regime. If we get to the very middle layer, to a little bit further out from the protostar, we start to have these icy regions. So where it's cold enough that these molecules will be frozen onto the grain surfaces again. And so this is really important where we have the ices, because this is where planets might be forming. One of the current theories is that where water freezes out onto grain surfaces is where we'll get giant planet formation, because having ices on those grain surfaces makes them a little bit stickier, makes them a little bit easier to adhere to, and maybe we could get from very small pebbles of solid material into planet-sized objects. There are hurdles to overcome in that process. We don't really understand completely how planets form out of these disks, but we're starting to have some idea. And understanding what molecules are here, what the ices are made of in these disks, will really give us an understanding of how those planets could potentially form. That could also be interesting because different molecules will freeze out in different areas. So you don't necessarily have a disk that looks the same the entire, as from the inside to the outside. You'll start to have kind of a heterogeneous disk. And so we might be able to understand what specific regions are useful for forming planets, or maybe are less so, and also what molecules would then get inherited into those planets. And so this leads me directly into our own solar system. So I really talked about other star forming regions, how we're looking at the star forming process in other star systems, but I do want to talk just a little bit here about our own solar system, because it's also giving us some clues about astrochemistry. So comets are thought to be pristine remnants of our early solar system, objects that are frozen, both in the fact that they contain solids and that they haven't been modified in billions of years. They're almost kind of frozen in time. We're able to do in situ measurements because they're so much closer to us than other star forming regions, to be able to look at kind of chemical tracers of how our sun formed, or of how molecules could potentially have been delivered to the early Earth. And so comets in our own solar system are giving us an understanding of what these disks might have looked like very early in the star forming process, or even what things could have looked like in the pre-stellar phases. So this is an image of 67P, Triumov Gerasimenko. I actually probably have not said that name out loud, so I apologize. I probably said it wrong. But this is a Jupiter family comet. So it's one of the comets that goes around our sun in a shorter period than some of the other comets that we see. But the reason why I bring up 67P is there was a paper a few years ago in 2019 that did a comparison of the molecules that we saw on 67P as determined by ESA's Rosetta mission, comparing those molecular abundances to what we see in the star forming region IRAS 16293. So here is one of the regions where we have actually seen glycolaldehyde, that sugar-related molecule. And this is also an interesting source because it is lower mass. So this paper used this source as kind of a sun analog, assuming that all low mass sources or sun-like sources would form in the same way. This paper, Drozdowski et al. In 2019, started to compare these two sources. And what did they find? So these are three of the graphs, just stepping through them. a little bit slower than probably to try to get at some of this information. So it's divided into 3 graphs just for 3 different types of molecules. So on my left screen, I have carbon, hydrogen, and oxygen-bearing species. In the middle, nitrogen-bearing species. And on the right, sulfur-bearing species. And then this graph is just looking at the star-forming region on the y-axis and the comet on the x-axis. And then just plotting their abundances to see how they correlate. And this paper found there are correlations between these abundances with a little bit of spread. That's especially true for the carbon, hydrogen, and oxygen-bearing species. We have a very nice correlation between these 2 sources. A little more spread in the nitrogen-bearing species off of this 1-to-1 line. And again, a little bit of spread in the sulfur-bearing species. And so even though this is only one source to one source, we don't know for sure if all stars form in the same way or if their environment, say, makes a really big impact on the molecules that we would see. This is a really interesting finding to show that the abundance of molecules that we're seeing in comets in our own solar system might be closely linked to what we're seeing in star-forming regions. So these molecules might be inherited from earlier stages in the star-forming process. Another limitation with this study was they could only look at the molecules that were detected in both. Lots of molecules have been detected in the star-forming region IRAS 16293, but there are a few more that have been detected in comets that we have not yet seen in star-forming regions. One of them was detected on 67P, and that is glycine, an amino acid, the amino acids that are important for making proteins. And I think just recently, probably most of you saw in the news that the comet Ryugu had found people had detected all 5 nucleobases from that comet. And so all the nucleobases that would make up the DNA and RNA, our own kind of genome. And so we're not quite seeing this level of complexity in star-forming regions yet, but we're seeing quite a bit. This field has come a long way, I'd say, in the past. Having a little trouble with my map here since the 70s when we really started to have that explosion of molecules being detected in radio waves. So is this the full picture? We have our beginning ingredients of hydrogen and helium that have, through the process of stellar life and stellar death, begun to form heavier elements. These atoms can come together in molecular clouds and in star-forming processes in order to create molecules, large molecules that could potentially be prebiotic. We have these molecules potentially being incorporated into planets as they form, potentially having planets enriched by comets, and potentially life being formed. If anyone knows why I put an apple pie here, please let me know. You'll get a prize, and that is just privilege of knowing you were right. So this picture of star formation and how it links to astrochemistry, or how it connects to interstellar molecules, is still just coming together, but I think we have a pretty good idea, at least a really solid foundation of astrochemistry. But I don't think the picture is quite full yet. There are some limitations with the telescopes that we have at the moment. They have really propelled this field forward, but for single dish telescopes like the Green Bank telescope that I showed before, they're really good at detecting molecules, but they're not really good at looking at the detail of these regions. They can't really get into the fine details of a protostellar source or of a protoplanetary disk to see where these molecules are coming from, but they are just very good at detecting molecules in reasonable observing times. So this graph here is showing the cumulative number of molecular detections by and split up by observational facility All of these 7 here are single dish telescopes, and they have detected so many molecules over the past, I guess this is 5 or 6 decades. Really big players in this is the 36-foot, the NREO 36-foot down in the States, the RM 30 meter out in Spain, now the Green Bank telescope out in West Virginia again, the Nobayama, I believe that's in Japan. All of these together have detected dozens, hundreds of molecules just due to their collecting ability. But we might need some finer detail in order to figure out what's going on. And for even larger complex molecules, when their emission is very, very faint, we might need a little more sensitivity with our telescopes. The other kind of limitation that we're running into is with interferometric telescopes. So collections of dishes that have their data pulled together in order to get higher resolution images on the sky, such as the Atacama Large Millimeter Submillimeter Array down in Chile. ALMA is at a bit smaller wavelength, light at millimeter wavelengths compared to other sources that use centimeter wavelength light. At millimeter wavelengths, we have what we call line confusion. So the data can be so rich in spectral lines that it's really hard to pick apart what these lines actually tell us and what molecules these lines are actually coming from. We reach a limitation in the amount of information that we're actually able to pull from this spectrum. So we have this, the lines get a little bit confused. At millimeter wavelengths also, the light is not as good at penetrating through dust. So if we have dust in denser regions, in those near those protostellar objects or in the disks, dust can get in the way of us actually being able to do our observations. So just a few limitations that we're finding with our current telescopes, even though they have been absolutely amazing, world-class in terms of allowing us to do astrochemistry. That leads me into the future of this field. So up next, we have 3 very exciting telescopes, or 3 very exciting upgrades happening. First, we have ALMA. Again, that array of dishes down in Chile is getting a sensitivity upgrade. So it will be much more efficient at doing the observations that it is already so good at doing. We have the square kilometer array, an array that is being built in South Africa and in Australia. It is going to be down at much lower frequencies than ALMA, really observing those very low energy things that we see in space. In between those 2 frequency ranges, at the centimeter wavelength range, we're going to have the next generation Very Large Array. So you might have heard of the Very Large Array that is down based in New Mexico. If you've seen the movie Contact, that is the telescope they use in there. But the Very Large Array is having an overhaul done on it. This next generation Very Large Array is also going to be based in New Mexico, but its array is going to spread into likely northern Mexico, up towards Canada. It's going to have lots of different configurations that we can use to find some really, really small details on the sky. And so just to give you kind of a different picture of how those telescopes will come together to create a very nice future of astrochemistry, we have the SKA in blue here, the NGVLA, the next generation Very Large Array, in yellow, and ALMA in orange. And this graph is showing us what wavelengths on the x-axis these telescopes will look at. And on the y-axis, the angular resolution that they can see on the sky. So going at lower parts of the y-axis, that's finer resolution. And so these telescopes are going to be very complementary in what they show us on the sky. They're going to cover 3 different but very important frequency ranges in the radio in order to show us so much about the molecules that we're going to see. And hopefully the NGVLA and the SK will be able to probe through that dust and show us what's happening, say, in protoplanetary disks. So there's a very exciting future. Hopefully we'll know more in the next decade about these. I think almost supposed to be coming online around 2030. But this should be a very exciting time up ahead. And so I just want to end here with why do we do this? Again, going back to Brett McGuire, I saw a presentation from him a few years ago, and he really summed it up perfectly. The fundamental driving question of astrochemistry is how do you make a cat from hydrogen and helium? How do we get the kind of precious life that we see here on Earth from the ingredients that came from the Big Bang? And astrochemistry is our key to doing that. So astrochemistry focuses on the molecular processes in the universe, and it's a really powerful look at the physical environment that we're looking at and the evolution of how they got there. And it really is a glimpse into our own cosmic origins. And I'll stop there. Thank you.
Thank you, Pamela. I think we have some time for a few questions from the audience. If anybody has any question for Pamela?
Oh, I'll go over here.
I can't see anybody.
All right, so we got Jeff here with a question for you, Pamela.
Okay.
Well, it's not so much a question. It's your thing with the apple pie. So I'm
Yes.
just taking a stab here. It's an episode of Cosmos with a montage of making an apple pie, and Carl Sagan says when the pie is put in front of him, to make an apple pie, you must first create the universe. Is that what the apple pie is about?
That is exactly it. You're correct. Great work.
Okay.
Thanks, Dr. Freeman, by the way. That was super interesting.
Thank you.
I have I hope I don't make myself sound too stupid. I'm going to use I think it's maybe an antiquated taxonomy here, but we used to categorize stars by metallicity. And so we used to have population 3, which was low metallicity, and then population 2s that were formed from, remnant of population 1 stars or some of their molecular clouds, right? And then we had population 1 stars with high metallicity. And so my question is just around the complex molecules, would it lead one to conclude that population 1 stars with a high metallicity would have more complex molecules than, say, like a population 2 or 3 star?
Yeah, that's a really interesting point. That I think, yes, you could assume that just given the kind of ingredients that you would have to make these stars, you could potentially have a kind of more complex chemistry. You could start to form some of these molecules. One of the limitations in studying that is we've ever observed a population 1 star that definitely would be, from that pristine hydrogen and helium gas. So we wouldn't expect to see any, complex carbon-bearing molecules. But even looking at other galaxies and looking to kind of maybe lower metallicity areas, we don't quite have the resolution to see necessarily these star regions in such detail. People are starting to observe those hot protostellar sources in external galaxies to start to see things like, methanol in those sources, to try to start to see if other galaxies have the same star forming processes as we do here. I don't think I have enough information to answer your question directly, but it is a really interesting thing to look at. There are different regions also within our own galaxy that have different metallicities. But again, our observations in this field are limited to where we can see in kind of high detail what's accessible to us. And so sources like the Taurus molecular cloud I showed before, Orion, Cygnus X, also Sagittarius B2 in the center of our galaxy is a really, really well-studied source. But say something like in the center of our galaxy might not have the same composition as something at the edge of our galaxy. So we're starting to try to branch out a little bit more to see if the different metallicities areas in our own galaxy would show us something different. So we're actually on the right track of where current research is going and trying to figure out.
Great. Okay, thank you.
Hi, thanks for an interesting talk. I noticed your list of big single dish radio telescopes did not have Arecibo, and that decades was the biggest single dish telescope in the world. Is there a reason that Arecibo did not contribute, or was not on your list anyway? I'm assuming that means it did not contribute to this field.
Yeah, so my understanding, so these are the kind of 7 dishes that really are big players in this field. And that is also due to the instrumentation that is on them. So not all radio telescopes would be, I think, equipped with the same ability to observe the same things. And so having you would also need a good spectrometer on these instruments in order to actually tease apart that light into its frequencies and start to figure out the chemical makeup or the molecular makeup of a source. And so I think that's just due to the different strengths of these telescopes. So yes, Arecibo is a big player in radio astronomy, but not necessarily in this specific field.
Okay, we probably have time for one more question if we have anyone who has a question.
Yeah, if there's anybody online that has a question, just ask Pamela your question now.
I was wondering, it's a great talk, thank you. I was wondering, we had a lot of interest last year in the interstellar comet 3I Atlas that came through. There was some information that there was differences and what we were seeing was different than what we expect. Now, is there any published research on what those differences really were and what the significance might be for the solar system where it came from, how it differed from what we know here?
Yeah, so that research is starting to come out. So there were radio observations done of 3I Atlas, say from ALMA, looking at that kind of molecular composition that we could see. I haven't gone really deep into the details of that research. It is quite new. But we are starting to see how it potentially is. They're starting to do comparisons of how it's similar or different from comets in our own solar system to see if kind of the molecular makeup of that disk could be the same or different, and starting to see kind of the, I believe, the heterogeneity of the nucleus of that comet. If you start to see this outgassing, starting to give off different molecules at different times as it's flying by the sun, that starts to give us an idea of how it's actually made up, kind of physically, in a structure, rather than just the, listing off the molecules in there. And that also gives us an idea of how it could possibly have been formed and where it could possibly have formed in its own disk. I do have to look into that, though. It is very exciting work that they were able to actually capture 3I Atlas with our telescopes in the short time that it passed by us.
Thank you very much. And Dr. Freeman, we thank you for your very interesting presentation today. And if when you decide to come back to Edmonton for a visit, see if the timing is right to have you actually in person.
I will be very happy to be there in person. Hopefully it's only a matter of time.
Great. Thank you very much. Okay, we'll be moving on to our next agenda item, which is the Observers Group report from Murray Hunt.
You may have noticed it's been pretty cloudy lately, all winter. We haven't been doing too much observing lately. Okay, here we go. Visual observers, stargazers. We do 3 main things. We have a monthly Zoom chat. Whoops. In-city get-togethers and dark sky sites. When we can, and when close to a new moon, hopefully once a month. Okay, so in March, we did a bit of a survey. We had 35 people responding just about what observing equipment is used with our club. And do you use binoculars? Well, almost 85% of the responders said yes, we do. I find that not unexpected, actually, but quite interesting. No matter how sophisticated telescopes we may have, binoculars still have a purpose, and they're very handy, quick to use. Here are a few of the suggestions people use, and mostly over 8-9 power without using tripod. Those image stabilized binoculars are awesome. I've only seen through them. I certainly don't have one. They're starting to get expensive up there. Oh. Do you own a telescope? Yes, 91% of us do. 91% of those responding. Any surprise there? Not really. I'm more interested in 9-10% that don't. I'm wondering if that reflects maybe new members, increasing our numbers. I don't know. And here's a rough breakdown. 38% people use reflectors. You can read it there. They're not that much different. Reflectors, refractors, SETs, and MACs. Just interesting. Oh, the last question. People had a lot of fun with that. What would you use for? Well, some hopeful people, they'd like to use the James Webb telescope. 5 people were quite happy with what they have. One responder thought that, well, a scope that does most things well, fairly light, easy to set up and use, sounds pretty ideal. Well, for our March 24th Zoom meeting, I planned to address that response. We put together a panel of 5 guest speakers and to present their personal story on their favorite equipment. You see. So Greg Bounds, Jeff Robertson, Luca Benzella, Trevor Robert, and Rory Paulson all spoke on their favorite equipment. And then thanks to Jeff Robertson, he's uploaded that onto the Edmonton Center YouTube channel. So it's available for everybody to see. This link is published in the this month's Stardust as well. And I encourage you all to go and have a look at that. It's about an hour and a half meeting. And our next Zoom meeting, Tuesday, April 21st at 7 p.m. Everybody's welcome. Thanks very much.
Okay, so I'm just going to switch things up here a little bit, Frank. We'll put the trivia up. No, we'll do the trivia now. Give me the trivia. So we have the 3 questions this month. First one is, how long does each season last on Neptune? Second question, what is the only planet not named after a god? And which planet do not have a natural satellite? So those will be answered after the break. And Frank, if you can bring up the RASC Edmonton apparel item. Jay Lavender has gone out and has got a deal with a local manufacturer here to provide us with some RASC Edmonton apparel. And I'll ask Jeff and Jay to come up and they can walk the, yeah, come on up, just see what you got. Because we're looking at jackets and polo shirts. So as you can see, Jeff here is wearing the...
I didn't practice my runway
Oh,
walk.
you didn't do the runway walk, okay. You got to do the spin. And Jeff was wearing the polo shirt that's available. Jay has brought some order forms, so if anybody's interested in looking at one of those two items, you can touch base with him at the break, and he has order forms, and he can explain the details to you. And I think they look pretty good.
Yeah, the coat.
But, yeah, Jay and the coat both look good. Okay. Okay, so again, touch base with Jay at the break if you're interested, and he'll give you the details. Okay, thanks, guys. Okay, we'll have the break, and then we will get back to the business at hand. Thank you. We'll get started again here. First item on that, the outreach opportunity. As always, I'm going to be reminding people every month to, if you're a volunteer, check the logistics webpage to see what's happening and going on. And if you're not a volunteer yet, if you're interested in volunteering for outreach programs, you can also get started through that same webpage. Our Scope Loaner Coordinator is a new guy, Trevor Robert, has taken on that position. And we're going to be doing this weekend, we're doing on Saturday, a inventory of our storage locker, which includes all of the telescopes which are in there at the moment, which take up more room than to get in there. It's kind of walking through a maze at the moment, but we'll get that up, and hopefully the program will be back up and running by the end of the month. Okay. Also, two announcements that are not on there. We have Susan Bram, who is going to give us a quick update on the Northern Prairie Star Party, followed by Kent Martin and a quick update on the Planeway project.
Thanks, Clayton. We wanted to give you an update on our planning so far for the 2026 Northern Prairie Star Party. Yes, it's well underway. The first thing is to save the dates. We're talking Tuesday, September the 8th to Sunday, September the 13th. That's the week just after Labor Day this year, so it's early in the month. And with the workshops on Friday the afternoon, September 11th, and a full afternoon of speakers on Saturday the 12th. Of course, on top of that, solar observing, BNLO nighttime viewing, that's Black Lake Observatory, T-shirts, the swap and shop on Saturday morning, and the barbecue on Saturday afternoon. So we've got all those elements in the works. Second, we wanted to let you know that we've confirmed two of our speakers for Saturday's program. We will be hearing from Yang Shen, a newly arrived assistant professor of physics at the University of Alberta. Thanks to Sharon Morsink for helping us to get in touch with him. Yang is a space weather and aurora researcher who will be talking about his current research. He has a number of years' experience with NASA and has just recently come out from California. And we are delighted that our Jeff Robertson has graciously accepted our invitation to be our keynote speaker this year. We have invited Jeff to celebrate the recent success of the Artemis II mission to the moon and back, and looking back on the history up to this point and next steps. So Jeff, we're just delighted to have you as our keynote for this year. And you can guess perhaps what the T-shirt might be looking at too, being an Artemis year for events for this year. We're working on getting our third speaker as well as details for the Friday afternoon workshop. So more in the next Stardust. Our team is also working on a number of other tasks for this year's event. The registration page is being updated thanks to Dave Mussel and Carol, and we will let you know when registration will go live in May. Marie Paulson has agreed to put together another set of observing lists after the great success of the ones he developed from last year. So great, thanks Marie for that. And then there are door prize solicitations that are going out to our generous corporate sponsors in the near future as well. So stay tuned for more details on the website and in the May issue of Stardust. And I'm speaking on behalf of our planning team, which includes Carol and Dave Mussel, Marion and Alan Hobbs, Rick Bram, and myself, Susan. If you have any questions or need more info, please get in touch with us. Thanks a lot.
Thanks. Okay. Good. Kent, you're next, and then Murray Paulson would like a minute as well.
Thanks, Clayton. Just a brief note about the progress on the Plane Wave project. We've been going like crazy. We got the computer mounted on a scope. Brian Martin has a Ritchie Chrétien with a very similar, slightly different model of Paramount. So that is all going very well, and that allows us to learn how to use it, basically. It's the software on our system is going to be based on the normal Sky, the 64-bit edition, feeding into Voyager software, which is a scripting and remote control facility. And it's fairly complicated, and it'll allow us to do scripting and control over anything you can think of on the scope or the mount or the observatory, or for that matter, the data from the CloudWatcher environment weather monitor feeds into it as well. And that will allow us good remote control over the telescope system. Other things we're working on, we're building a set of environment controls for our equipment boxes. Because we're in a remote control situation, we're fairly concerned about safety. We don't want the power to die and then to have it start raining. That's a bad combination. So feeding in weather information, a UPS that will give us enough power and enough time to close the observatory. And when the weather is horrible, like it has been for the last while, although we're getting out of winter, we're also concerned about cold weather operation for particularly our electronics. So we'll have all our electronics, our computer system, switch, router, and all the rest of it, network storage, inside temperature and humidity controlled boxes. So we're working on that as well. So that's where we are at the moment. We're just waiting for other things to happen, like money, and then we'll make further progress. Thanks.
Thank you. Okay, Murray.
Good evening. The Astronomy Day for St. Albert will be held on the 24th, 25th of April. There's a Friday, Saturday night. And if anybody would like to join us at City Hall, we usually are just on the walkway behind City Hall, just, I think it's north of the courthouse in St. Albert. So any of you out there that are interested in coming along, you can give me a call. I'm the Observer's or new members advisor. You can hit that button on the website and send me an email, and we'd be welcome to have you join us. Thank you.
Okay. Book of the month, and we will get Mark Zelsick up here to tell us what the book is for this month.
Oh, there we go.
Stuck up behind.
Good evening. Greetings from the Lamplighter Library from co-librarians Rosemary Ball and I. Library is situated just before you get into the Story Theater. Books are available before and after the meetings. So there's two ways you can check out the books now. You can come to the meetings before or after the meetings and look through the library, or you can forego the small talk about dulcimer music and just check out online the book catalog. By doing that, simply go to the Edmonton RASC website, scroll down to where you see library, and click on that, and then you can click on the link that will access all 700 plus books in our catalog. So two ways of looking at the selection of books. This month's book of the month is Parallax by Alan Hirschfeld. To the ancients, actually, I'll mention first that the book is donated by Grand Prairie RASC member Rene Gadaz. He donated a whole bunch of books recently, a lot of really good titles on physics as well. So we'll be slowly introducing those books into the library. So this is actually one of the books he donated. So that's Rene Gadaz. To the ancients, the stars scattered about the firmament on a clear night gave little indication of how far away they were. Perhaps the brightest stars look closer because of their luminosity, but it is easier to believe that all the stars were equally so far away that they represented the unchanging nature of the cosmos. Then came the likes of Galileo and Brahe, who mused that stars could be at different distances. How to measure these distances? Conveniently, the effect of parallax for measuring the angular distance of a star is provided by Earth itself, which, when situated at opposite ends of its orbit about the Sun, provides an effective baseline for measuring these angles, albeit very small angles. The book Parallax tells the story of how the later generation of astronomers, the likes of Friedrich Bessel, Wilhelm Struve, and Thomas Henderson, succeeded in measuring the parallax of, as it turned out, their own pet project stars. Only thanks to the advent of sophisticated telescopes in the late 1700s that could foster the required minute measurements. So as far as what stars they worked on to determine parallax, do we remember the three stars that first had their parallaxes measured? For example, Bessel. Any guesses? Very good, 61 Cygni. How about Wilhelm Struve? That would be Vega. And finally, Thomas Henderson. Here's a clue. It's in the southern hemisphere. Yeah, Alpha Centauri would be the obvious one. It's the closest star. Another star, Gamma Draconis, or Eltanin, was chosen in the late 1860s by the British astronomer and inventor Robert Hooke as a candidate for measuring parallax using his so-called zenith telescope, in whose field Gamma Draconis saunters through in its journey through the sky. About this star, Hirschfeld writes, "Tonight, in the eyepiece of my small telescope, Gamma Draconis appears as a fiery yellow-orange point. Radiant spikes boil up angrily from the starry image, as though it were a cat trying to claw its way out of a luminous sack. It's easy to become mesmerized by the scintillating image of a star in a telescope. Its light floods my eye, a silent siren's call that draws my consciousness deep into space. Soon I sense a connection between me and the star, as though its beam were a searchlight that had turned my way and was illuminating my mind. Gamma Draconis looks pretty much like any of the thousand of or so other stars above my head tonight. Technically, Gamma Draconis is a giant star. It's about 25 times wider, although somewhat cooler than the Sun, and radiates into space about 180 times more energy. It lies approximately 150 light years from the Earth, 900 trillion miles. The light now streaming into my telescope began its journey about the time Marx and Engels penned the last line of the Communist Manifesto, and a young Mark Twain dreamed of becoming a Mississippi River pilot. Tonight, as on any night, only an infinitesimal fraction of the star's photons are swept up by my telescope. Others sprinkle the aqueduct around me like fairy dust, their luminous energy dissolving into the ground as minuscule pulses of heat. Still others leave Gamma Draconis in the directions that carry them nowhere near the Earth. Some of these might be streaming into a telescope or sprinkling an aqueduct on another world. Nature is propagate with its starlight. Most is not destined for sentient consumption, but falls dumbly onto dust grains in outer space, or flies unhindered through the void. Little did Hooke realize that at 150 light years distance, Elton was hopelessly too far away to have its parallax measured by the rudimentary equipment of the time. But such is the nature of science, with much stumbling and toil on the journey to big discoveries. So yes, the book is available after the meeting, and actually, Lori Walton returned the book on Gemini, which was the book of the month last month. So that book is available right now as well. Great, thank you very much.
Okay, Astro Imaging Corner is next, and wait to see what Tom gets online here, and away we go.
Thank you. Okay, so welcome to Astro Imaging Corner 155. We had a lot of submissions this month, so some of you had multiple submissions. If some of those submissions didn't make it into this one, rest assured I will use them in future AICs. So the cover picture is the far side of the moon and a crescent Earth, captured by one of the Artemis II crew on April 6th. Not sure exactly which of the cameras that they used, but their most popular one was a 10-year-old Nikon D5 DSLR camera, which is pretty cool. The image was stacked with AutoStacker 3 and processed using Registax. I'm just kidding. So that's the cover photo for this AIC. So this picture was taken by Berta Beltran on Friday, March 27th. She says 1 week after the spring equinox at 7:40 a.m. using her trusty Fuji X100VI. She says, I've done some cropping and very minor processing, but other than that, this is pretty much how things looked that morning. And the picture is just straight out of the camera. And Berta, I love this picture. You know, they say every picture tells a story, but this one seems to be the introduction to a novel. So well done. And this is a contribution from Brian Martin. It's Welsh House. He says, this is a 3-panel panorama taken of the historic Welsh House south of Rosalind, Alberta, on one of those rare, warm, clear evenings this winter. Image was taken February 8th, and each panel is a 120-second exposure at ISO 800 using a 24mm lens and an Astro modified Canon 6D. So I love this picture. And so I would say if Berta's photo was the introduction to a novel, this picture would make a suitable ending. Well done, Brian. So this was Archimedes Crater and the Apennines by Murray Paulson. He says that it was taken with his AP 155. I take it that's an Astrophysics 155 using a 2 times Barlow and fire capture. It was then processed with the autostacker, producing an image using 40% of the 5,000 frames. Registax processed the final images with the wavelet processor. That's a very, very nice, clear picture. I've often said that the moon is a hard object that requires a soft touch when you're doing processing, and I think he's got it really in balance here. And here's a close-up that Murray also contributed. We also have a picture of the Apennines from L. Pancratz and Archimedes crater and the Hadley Rill. So Al writes, this large crater with the smooth-looking interior at the top center is Archimedes. It was originally deeper and had a central peak, but lavas that formed Mare Imbrium also welled up inside the crater and filled it part way, covering up the central peak. Near the upper right terminus of the Apennines, a yellow plus sign, and I hope you can see it, marks the spot where the Apollo 15 astronauts landed about 55 years ago. If you look closely, you will see a channel or rill that meanders southwestward from their landing site. That is Hadley Rill and is thought to be carved by ancient volcanic lavas. The mountains running from bottom left to upper right are the lunar Apennines. They were created about 3.9 billion years ago and form part of the southeast boundary of Mare Imbrium. At lower center is the tallest peak in the Apennines range, Mons Huygens, and I have marked it with a red caret. It rises 17,380 feet above the surrounding terrain. This image was taken on March 26th using a ZWO ASI 585 MC camera mounted on a 10-inch f6 Dobsonian. The video was processed by Planetary System Stacker and Affinity Photo 2 using the best 6% of 643 total frames. So a great picture and great information, Al. That's my dog scratching away, sorry. Preparing her bed on the floor before she goes to bed. All right, so this is another contribution from Murray, is the Io occultation. And he says, this triptych shows the ingress of Io it is occulted by Jupiter. And the last image is the best contrast of the images. I really love this triptych, and you can see Io there, and just finally almost gone. So well done, Murray. This is Saturn by Murray. He says this is one more from last fall that didn't make it earlier. It was shot on September 26th at 6:47 Universal Time. Again, it was taken with his AP 155 using a 2x Barlow and fire capture, and then processed with autostacker using a best 40% of the 5,000 frames. So this is a contribution from Hans Johns, and this is the Tadpole and Flaming Star Nebula. And he's taken this in RGB. This was taken from Bortle 7/8 skies in Sherwood Park with the ZWO ASI 2600 MC Pro camera. And the image acquisitions were controlled by Nina and images processed in PixInsight. So he says his intention was to generate an image in the Hubble palette, but it turned out that it looks quite nice in RGB despite the relatively short exposure time of 2 hours only. So I'm attaching both here for comparison. So I'm going to show you the next image is in SHO. I want you to look at the blue reflection nebula in the RGB photo surrounding AE Aurigae, and then see if you can see it in the SHO palette and the narrowband, which I'm going to show you right now. See, it almost disappears. Beautiful shot, but reflection nebulae, if you're going to try and get reflection nebulae, you have to use RGB. They just don't emit like emission nebulae do, which you can capture using SHO. The SHO version, he says, was exposed significantly longer for 11 and a half hours. And both were imaged with an APO refractor at a 520 millimeter focal length and a focal ratio of f/4.2. Great work as usual, Hans. So this is a shot of the Heart Nebula, IC 1805, from Brian Martin. It was taken November 14th, 2025, from he says, his light polluted backyard 10 kilometers east of Sherwood Park. The image was produced using a ZWO ASI 294 MC one-shot color camera and a 70 millimeter stellar view refractor at 376 millimeter focal length and a total exposure time of 66 minutes. And this is the Heart of the Heart from Brian, which he did in SHO. And he says, by way of comparison, here is IC 1805 in narrowband. And this was taken a lot long ago. This was taken back in October of 2019 using a 102 millimeter stellar view refractor at a 712 millimeter focal length, just over 6 hours of exposure using a ZWO ASI 1600 millimeter camera with HA03 and S2 filters. Again, from his Bortle 5 skies at home. And that's a beautiful picture, Brian. So this is from Ray Wiens, the Christmas tree or cone nebula, and it's from this last winter. He says it was shot with a ZWO 2600 with an APS-C size sensor attached to the William Optics 132 FLT triplet mounted on an iOptron CEM60. The data includes about 42 images of 300 seconds each on a night which ended at -17. It was stacked in APP Astropixel processor and processed in Lightroom. He says, I was hoping to get more data, but the winter did not allow for it. And here we have the Seahorse Nebula. It's a dark nebula. It's also known as Barnard 150. It's a dark molecular cloud in the Cepheus constellation about 1,200 light years from Earth. The image was shot with the ZWO 2600 camera, again mounted on that William Optics 132 FLT triplet, and on the iOptron CEM60, with guiding occurring through the main scope. This includes 48 subs at 300 seconds, stacked in APP and processed in Lightroom. Very nice, Ray. And this is also from Ray. It's M81 and M82. And he says this constitutes about 2 hours of data with 5-minute subs. Again, with the FLT 132 and the CEM60 and the ZWO 2600. It's processed in Lightroom and stacked in APP. And that's a lovely shot, Ray. So this is Alan Hobbs's contribution. The Pinwheel Galaxy is he says, Messier 101, is a face-on counterclockwise intermediate spiral galaxy located 21 million light years from Earth in the constellation Ursa Major. It was discovered by Pierre Méchain in 1781 and was communicated that year to Charles Messier, who verified its position for inclusion in the Messier catalog as one of its final entries. On the 10th of April this year, I set up my Seastar S50 in equatorial mode using a Skywatcher wedge on a photo tripod and shot M101 on my driveway in West Edmonton. 78 subs at 30 seconds for a total exposure time of 39 minutes. I processed this photo in Astrophoto and PixInsight from the stacked bits file. And, you know, M101, it's a big galaxy. It's a bright galaxy, but it's hard to image. And I'm really pleased to see how he was able to get the more faint outer arms, which are sometimes problematic when you're processing it. So well done, Alan. So please send me your images, and I want to say, come on, Seastar Army and similar, send me your images. If I get enough, I promise I'll devote an entire session to images captured with these remarkable imaging systems. So don't be shy. Send them in, and let's have a session totally devoted to the Seastar type electronic imaging devices. Thanks very much.
Okay, so you're here at a challenge for the Seastar or Smart Telescope crown. See what we can just get into, Tom. Okay, get Frank to put the trivia answers up, and then we'll do the final announcement. Okay, how long does each season last on Neptune? More than 40 years. What is the only planet not named after a god? Our home planet Earth. And which planet do not have a natural satellite? That's Mercury and Venus. Okay, final announcements. If you put the cartoon up, everybody will definitely relate to this. Consensus being over the last 3 months is that this has been what we've been trying to do to get anything out there. It has been cloudy more times than not. 3 times I went out with the Seastar, and by the time I got it set up, the clouds had moved in. So, and that doesn't take long, 10, 15 minutes, and you're ready to go. So hopefully it'll clear up here soon. Not going to bet the house on it, that's for sure. Okay. Okay, the next meeting will be Monday, May 11th, and it will be a members' night. Lori Walton has already confirmed that she will give us a SETI update. So we're looking for 2, maybe 3 more people who want to do a presentation on the on May 11th. Just send me a email with that information, and we'll get you involved. And then this coming April 25th, Saturday, is International Astronomy Day. Here at Telus World of Science, we'll be set up in the lobby with a RASC booth, and we invite anybody who wants to come by, see what's going on. You're welcome to attend. Hope everybody shows up. And if the weather permits, and that's a big cross your finger. If the weather is good, the deck will be open for some solar observing. And well, after that, I'm not going to hold my breath on that one. Anyhow, that's it for tonight. And we look forward to seeing you on May 11th for the next meeting. Thank you very much. Yes. What's that?
Telescope.
Oh, good. We're also going to have a scope clinic. So anybody who needs some help with their telescopes, definitely bring them down, and we will see if we can get them working for you if they're not, or give you some information how to use them better. Who's going to be running that, Jeff? You?
Hey.
You may as well come up and explain it.
Thanks. Yeah, okay. We've got enough people for the booth. They've signed up through VicNet and that. But we would like to have a couple people help out with the telescope clinic that Jay is going to be running. Weather permitting, we'll have our tent set up next to the deck. If the weather is not good, and I volunteer at RASC on Saturday, and the weather on Saturdays always seems to be the craps. But anyway, if it's inclement weather, we'll have the telescope clinic inside. I'll be putting a notice on our website and on Facebook for anyone in the general public to come by if they're having scope problems. Come talk to us, and we'll get them on the right path.
Thank you, Jeff. Okay, so that's it for tonight. So hope it stopped raining by now and it hasn't started snowing. Okay, we will see you in May.